All right, guys, I'm preparing my desktop and should be ready within 1 or 2 minutes. And at this time, so I will not share my screen with you, but shortly. Okay, so give me some minute. Okay, now I think I'm ready. Just hiding away some windows, including the emails and the calendar. Okay, so first of all, for today's class, we have several homework questions to go. And for these homework questions, I deem them important as understanding the core concepts of the CS540 operating system. And at the same time, since we did the quiz number 2, maybe we will start with our quiz number 2. And before that, I'm going to run a poll quickly. So I gave you 30 minutes on quiz number 2, right? And how was the time? If you think so if you think the time is sufficient, you can choose the time's good. If you think you need more time, so you can choose it's overwhelming. And based on this info, so I will be able to adjust the quiz time and the questions accordingly. Okay, and I'm going to find my quiz number 2, which is from here indeed. Okay, all right, so got the quiz number 2. So, okay, overwhelming. Yeah, I got one overwhelming. 2. Okay, I'm going to end the pool in 3 seconds. 3, 2, 1. Okay, and then so you can tell for most of you, you think it's okay. So that means, well, so I hope we get the questions, and I will think the 30 minutes will be sufficient for the quiz, and I will not make that adjustment. Here's the question. So consider the following page reference strings. 72312, so this is a string. And don't you think it looks familiar? Guys, where I get this info? Where I get this info? This is directly from the homework, right? So almost the last homework, but we have a homework due today. So this is from the previous homework, and exact the same string and exact the same algorithms. But what's major thing that I've changed? What is the major thing that I changed in this question? That is, instead of 3 frames, how many you have now? You got 4 frames now. You see that? This will be the core part to this question. If you still adapt the 3 frames, then you will not have the correct answer, because we now have four frames, and then you need to use the new 4 frames to think about how to resolve the page faults according to the page replacement algorithms here. Okay, and of course, so the answer will be dramatically different from your previous homework. Why? Because of this issue. Okay, so now we got 4 frames, and consider your homework question only 3 frames. And I have this part highlighted. I hope that everyone's captured that. And if you miss this point, well, then so pretty much you miss the question. Okay, now so let's draw. Let me see. So what is the best way to represent that? Maybe I will use my Xcode draw here. Okay, so and first I would like to consider. So this is what? This is my string. So page reference string here. Okay, now I got a string copied. And also I need to know what? I need to know I should have 4 frameworks here. Okay, 1, 2, 3, 4. Okay, now this is my 4 framework, and I will copy this part over, and then so as a reference here. Okay, so now this will be the reference. Okay, so to deal with the first number, which is 7, and of course it is not inside our frame, right? My bad, it's not inside our page. So what should we do? We will say, hey, so we are going to load the 7 here, and at the same time, so I'm going to count what? I'm going to count the page fault. Okay, so number of page fault. Number of page fault, and which algorithm would you like to go first? Well, so for these three, of course, we will do it one by one. So what is the LRU? So the least recently used algorithm. Okay, so the least recently used algorithm will be the LRU. And we will say, how about this first in, first out? Well, so it should be replaced with first come, first serve, right? So, and so this we will just go over it one by one and replace the one that is sitting there for long. And how about the optimal replacement? Well, the optimal replacement will look towards the future. Recall that it will look towards the future and try to figure out what will be the what page will not be used for the longest time. We will have it replaced. Okay, so recall this is for the optimal replacement. And then so for the LRU, we'll look from the previous past and see, so what is the least recently used? And that is according to the history. From the left, we will be able to pick out one candidate and have it replaced, okay? Now, so the first one, so let's do the LRU. And maybe we will do the first one, maybe we will do the, not the LRU, but the first come, first serve, because this will be the most straightforward one, okay? Number of page fault for the first come, first serve. Okay, now I can count 1 here, and let me see. So how can I represent the value here? Okay, so is there a quick way to, maybe we will just call the add 1. Okay, now quickly add 1 here. Okay, now, so, and the answer will be, what's going wrong? Okay, so 1 plus 1, 1 plus 0. Okay, now 0 plus 1. Okay, 1, 2, yeah. So this can be used as a counter. Okay, so plus 1. So this is when we load the 7 here. So you can tell it is 1 page fault because 7 is not here. How about the next one? The next one would be 2. And what I can do about it? Well, so I have to load the 2 into my page here. Okay, so now 2 is here. And of course, I will need to increase the counter by 2. Next one, it will be 3, and I will have space and I will load 3 here. Okay, now, so increase, oh, my bad. So increase -1. Okay. Now this is a 3. And then so next I will call the +1. We have 3 page faults so far, and that corresponds to 7, 2, and 3. How about the next one? Next one will be 1. So, and then so I will have, well, this is too sensitive, right? So 3 plus 1, yeah, so we will get 4 page fault here. Okay, make sure that I don't touch the enter key too many times. Okay, so we are done with the first 4 numbers, and they will cause 4 page faults with, and so unless we have repeating numbers inside them. Otherwise, we will have 4 page fault directly from the first 4 numbers. Okay, how about the next one? The next one will be 2. And do we need to erase anything and load the 2? No, the 2 is already there. So what do you say? So this is not a page fault. So we still have 4 page faults. Okay, and comparing the next number, guys, I'm done with this 2 here. So because this 2 is resolved from the previous 2 in our page table. Okay, so the next one, it will be 5. So what do you do about this 5? Well, so we have to replace some pages from this table, and it will be the 7 here. Why? Because it's the least, it is the oldest loaded element 7 here. So we will have it replaced with 5, and that will cause a page fault. So I'm going to increase the page fault by 1. Press enter only once. Okay. Now the next is 3. Will that cause a page fault? No, because this 3 can be resolved with this 3 here. Okay. Next value, it will be 4. So what do we do about 4? Well, so I'm going to replace the 2 with 4, so that will cause a page fault. So I'm going to increase the page fault count by 1. Okay. And then the next one, what is that? It will be 7. So what do we do about 7? 7, I'm going to replace 3 with 7. And then, so take a look. For the 7, so that will trigger a page fault. So increase the counter by 1, 7. And for the next 7, did I skip 6? Yes, it seems I skipped 6. Oh crap, what do we do? So then let me restart. So what's the number before that? What's the number before that? It should be 3, right? And I don't like that. So one mistake, so you have to start not almost all over again. So 7, if I recall, 7, 2, 1, so 7, 2, 3, 1. Yes, 7, 2, 3, 1. And then so replace 7 with 5. That is from here. And replace 4 with replace 2 with 4. Yep. So and I'm counting on 6 and now. So I need to replace 6 with what? I need to replace 3 with 6, okay, because 6 is on demand. And here, so let me try to bring the history. How can I bring out the history here? Is there a way that show me the history? Oh, when I expand this window, so I should be able to see the history. Nothing saved in the memory. Okay. So show me the history. That is what I need. Okay, you don't want to show me the history? That's fine. So let me count 6. So plus 1. Yeah, I think I'm good on this counter. Okay, I think I'm good on this counter. Now it is just about the next number, so which is the 7 here. So what shall I do about it? So thanks for the reminder. Otherwise, the answer will be incorrect. Okay, appreciate that. So I should replace this one with also with 7. Okay, because I get the request for the 7 here, and that will also satisfy. And I need to increase the counter. Okay, let me increase the counter by 1. And this 7 will satisfy the request for the 7 with no problem. And on the 0, well, so I don't have 0 in the table. So what do you do? You have to replace this element 5 with 0. Okay, and then so increase the counter by 1. So what I get? I get a 9 here. Okay, that is 9 page faults. 9 page faults from for the FCFS algorithm. Okay, 9 page fault from the FCFS algorithm. Okay, let me. Okay, 9 page faults. All right, so this is for the FCFS. How about the rest 2 algorithms we need to deal with? LRU. Okay, for the LRU, let's take a look. So I'm going to start from here for the LRU algorithm and see how many page faults will we have here. Okay, again, so I will reset my counter to, I will use my calculator as a counter and reset it to 0. Okay, and then so plus 1. So when I press enter, so that will count the first one. Okay, now clear the page table and start all over again. Okay, so the first element, it will be 7, no problem. Okay, and for the next one, it will be 2 and increase the counter. For the next one, it will be 3, okay, and increase the counter. And for the next one, increase what? Increase 1 here, okay, and this is 1 and increase 1 here. So the first 4 elements, they will trigger 4 page faults, no problem. Okay, guys, the next one, which is this 2 here. What shall I do about it? No page fault because it can be served from the 2 here. The next one, which is 5. Guys, tell me, where shall I look for the 5? Where shall I look for the 5? Well, you are going to say, hey, which element I'm going to replace? Now I got a 7, 2, 3, 1. I got a 7, 2, 3, 1. You can tell the 2, it's being immediately used, right? So the least recently used, I would say 2 is the most recently used. So I'm not going to replace 2. How about the 3? Well, for the 3, it's being used here, okay? And how about the 1? The 1's being used here. How about 7? We can tell among these 4, 7, 2, 3, 1, 7 is the least recently used element, okay? So what do you do? I'm going to replace 7 with the new element 5 here, okay? And at the same time, increase the counter by 1. This is resulted from the 5 here. Now the next one, I don't need to replace anything because 3 can be served, okay? And for the next one, which is 4, so what do you say? I'm going to check these elements. 5, 2, 3, 1 will be the my candidates, okay? And I can tell 3 is being most recently used, and 5, well, so it is worse than 3, but better than 2 and better than 1. So what do you say? I'm going to replace this 1 with because it is the least frequently used among the 5, 2, 3, 1, and I'm going to replace it with 4. Okay, and then so at the same time increase the counter by 1, and this will be the process. Okay, now I'm done with 4, And what's next? Next, you need to deal with the 6 here and take a look. Which element shall I replace with 6? Okay, check the candidates. 5, which is here, 2 before 5, 3 after 5, and 4, the most recently used. So what do you say? What do you say? So you are going to replace 2 with 6. Okay, replace the least recently used algorithm. Okay, not the algorithm, elements. And then, so the 6 replaced the 2, and what do you do on the counter? Increase the counter by 1, so it will be 7, okay? Now to the next. Next, what do you say? So I need to find 7, but 7 is not in the table. And inside the table, I got 5, 6, 3, and 4, okay? So 5, which is right here, and 6, which is right here. 3 and 4, it's right here. So which is the least recently used? It will be 5. So what do you say? So you are going to replace 5 with 7. Okay, so replace 5 with 7. And don't forget to increase the counter by 1. Okay, now for the next 7, so we can get a 7 from here, no problem. And how about 0? Well, for this 0, you can take a look. You are going to replace either 7, 6, 3, or 4 with this 0, which is the least frequently used, least recently used, not frequently, least recently used. You can tell 7 is the most recently used, and 6 is, well, so it's not bad, right? So, and for the 3 and the 4, well, we can tell 3 will be the least recently used. So what do you do? You are going to replace the 3 with 0, okay? And then allow me to modify the 3 with 0 here, okay? Now, so and don't forget to increase the counter by 1. Okay, so what do we get? We get a 9-page fault. We get 9-page fault for the least recently used LRU algorithm. Okay, so this would be the answer. And of course, I ask you to represent every single step in your answer. Okay, and hopefully you don't just give me the result like a 9-page fault for that, 9-page fault for that. So. And I need you to show me every step, just like what I did here, but not in the animation, but in multiple copies, so that I know, so on each step, which number is being replaced, okay? And I did the step-by-step, which takes more space for sure, so in my class representation. And here today, we have multiple questions, so I will not just spend the whole class on this one, okay? Now to the last algorithm, which is the optimal replacement, And which direction we are going to look for? We are going to look for the optimal. So of course, to reach the optimal, you need to look at what? Look at the future and make not a prediction, make the preparation for which will be used, okay? And of course, we will start with 7, okay? And 2, and 3, and 1 all loaded into the table, and that will give us what? That will give us the 4-page fault at the very beginning, okay? And then the next one, I will prepare the +1 later, okay? Now the next one will be 2, which can be served, and then the next one will be 5. Guys, now I need to load 5 into my table, and I need to replace 1 with 5. So I got 4 candidates, 7, 2, 3, 1. Which is the least, which is the, how can I phrase that? Which will not be used in a long time, in the longest time. The one not being used in the longest time. Let's take a look, okay? Now, of course, you will see easily that the 7, okay, it will be used here. And let me change a different color. Okay, 7, it will be used here, okay? And then, so how about 2? The 2, you can tell, now where are we? We need to load 5. We need to load, we need to load 5 into the table, right? Because 7, 2, 3, 1, yeah, 2 is being resolved. I need to load 5. And then you compare, where is the 2? Where is this lovely 2? Well, so this lovely 2, you can assume it is somewhere in the infinite place, okay, infinite far away, because we will not use, according to this sequence, we will not use this 2 at all, okay? And then, so how about the 3? Well, so you can tell the 3 will be immediately used after 5, so you'd better not unload 3 because you want to keep it there. And also there's another option, which is 1. So which one would you like to use? So now you have the option for 2 and for 1. I would say so. It is up to you to choose because that will not change the result. Okay, so and in my case, I would like to change the 2 because I load it up first. Okay, and delete the 2 and place this algorithm 5 here. Okay, so this should be in green, but it doesn't matter that much. Okay, now the 5's been loaded, and what do you do? Increase the counter by 1 so that we have 5 page faults so far. Okay. Now the next one, so you want to load the 3, and the 3 you can tell it's immediately there. You don't need to change anything. And the next you want to load 4, and which element shall I unload to make space for 4? Well, take a look. So now what we get here? We get inside the table 7, 5, 3, 1. Okay, and in the following sequence, you don't need to deal with what? You don't need to deal with 5 or 3 or 1. So which one you want to replace? You can say, so pretty much I will replace either. So any of them, so that will be fine. Okay, and I guess this time I will maybe have some algorithms, and I will need to make the judge, and I will say for any 3 of them, so you can choose to unload. Maybe I will just unload this 5 and make room for what? Make room for 4 here. Okay, now, so, and don't forget to increase the counter by 1. Now the next, so you can tell it will be what? It will be 6. I need to load 6 into my memory. Okay, now what is my candidate? I got 7, 4, 3, 1. Okay, 7, 4, 3, 1. And so which one you want to unload? So 7, you will use it immediately. And about the 4, 3, 1, it doesn't matter. So which one you want to unload? Maybe you can unload the 4 again and keep the 6 here. Okay, and then don't forget to increase your counter by 1. Okay, and then about the 7, you know, so it is inside the memory. And about this 7 inside the memory, about this 0, which one you want to unload? Well, so pretty much this time you can say, hey, maybe I will just unload the 7 and place 0 here. Okay, and don't forget to increase the counter by 1. Okay, so the answer to this question, it will be 8 page faults. Okay, so 8 page faults for the optimal algorithm. Okay. Okay, that will be the answer. 8 page faults for the optimal algorithm. Now let me address these questions in the chat. So I wondered about it a lot. I wasn't sure if there were priority. No, there is none. So because you don't need them anymore, right? So then just ask them to make space. Anyone will do. Okay. And I use a first in, first out if I have to choose between 2 elements. Yes, that can be used as well. And guess it's up to you to choose which element you want to replace each time. That's right. Just to make sure that you choose the one that will not be used in the relatively long time. So this will be for the optimal algorithm, right? So, and then, so we get the answer. And of course, I am expecting you to show every step. And so the verdict on the numbers, it will be 9 page faults for the LRU, 9 for the first come, first serve, and 8 for the optimal. Okay. Now, so do you get this question right? Okay, do you get this question right? If you think, well, so that is the number I get, and I have the result, I have the every step shown, then so that's a good job. If you say, well, so I don't get the exact numbers and I miss 1 or 2 steps, so I will look into your answer and find, so I try to get the max partial credits to you. Okay. I forgot to count the first page fault. First 4 page faults. Yeah, so that's a common mistake. You know, so think of the page fault. When you cannot find the page in the table, that is a page fault, right? So initially we cannot find them at all. So that's why so we will count that. But don't worry. So I will try to, as I said, I will try to get a good partial credits for the partially correct answer. Okay, and okay, so scan my hand-drawn figure and send it to. Okay, so that's good. So you don't, of course, you don't need to do the digital representation. And if you prefer to draw it out on paper, and make sure that the photo is compressed a little. Okay, so when I say the photo is being compressed, that is you don't want to send the raw photo from the raw JPEG from your phone or from the scanner. You know, so the size will be a concern. So say so if everyone generates 10 megabytes file. So for one submission, so that will create a lot of space, right? So, and for the Blackboard, so when the storage space are used to a good extent, so they are going to also bring some unstable issue, and it will slow down the speed. So usually I will convert the size to a smaller size, maybe less than 1 or 2 megabytes, and then send it. Okay, no problem. But if you're in a hurry, then what do you do? Forget about the size, take a photo and send it to the Blackboard. Okay. All right, so this will be our quiz question. Any question on that, on the 3 algorithms? Okay. Okay, so from our TA saying that memory is so the computer's memory is filled with homework. Yeah, that can be the case. You mean the storage, right? So you don't mean the memory. So for the 540, we take the difference between the storage and the memory seriously. So I guess you're talking about the storage. So, but for the storage, yeah, okay. Didn't we do the first in, first out? Well, so it is the same term as the first come, first serve. So of course you can replace it as long as you are using the same thing, like the queue here. Okay, when I say a queue, a regular queue, not the priority queue here, then it will be good. Okay, so the term, so from our textbook, well, so it's a bit inconsistent, don't you think? So in the text, in the paragraphs, it says the first come, first serve, and then in the questions, it gives me the first in, first out. Well, yeah, that should be resolved into the one term, right? So, but we go by the first come, first serve, and this is the same algorithm we use for what? For the disk head seeking algorithm, along with what? Along with the where else we learn the first come, first serve? From the process scheduling algorithm, right? So so this is just a common algorithm and easy to implement, guys. So I'm going to pause my screen share for a little bit because someone's sending me the message. Okay, good. So I don't need to process it, nothing urgent. Now I will go back to my screen share. By the way, so if you need to share your screen in some context, for example, when you are doing the presentation and when you need to demonstrate to your instructor about your work, then so I would recommend you to prepare your desktop. Like there's a way to hide away the desktop options, okay? And then for example, the view, you can get, if you are using Windows, show desktop icons. Okay, so choose this option to hide away something. And yeah, so there are some incidents like, so when doing the screen view or when sharing the screen, and some accidentally expose the personal info. And of course, this is not desired and not appreciated, right? So that's why. So I would say maybe you can prepare a desktop and then so close all unnecessary windows. So for the instructors, it will be also when you are doing the grading, especially for the quiz and for the exam. So please hide away students' score. You don't want to show that to the students. Okay. Anyway, so what I have here is I can show you with the CS540 homework 5 to 8 solutions. Okay. I don't get every question done because I know, so you are still working on the homework number 8, right? So what is the due date? The due date is today, right? So I will not reveal the answer from the homework 8. But for these homeworks, these homeworks 5 through 8, maybe I will just change the title. 5 through 7, they were assigned after midterm, okay? That means, so with some good probabilities, we will see something similar in your, not the quiz anymore, in your final exam, which is scheduled in the finals week, okay? And yeah, so username and password, but the password should not be visible to the viewer, right? So it should be represented by either the star or by the blocks, right? So, but we will see. Okay, so hopefully, yeah. So everyone's aware of that. Okay, so let's see. So homework 5, question number 2. Recall that homework 5 is from which chapter? It's from chapter 6. Okay, what is the main topic in the chapter 6, guys? So recall what we discussed in chapter 6. Well, we discussed about the process scheduling, or if you prefer, CPU scheduling algorithms from chapter 6, right? And then so we talk about, hey, so if we have a bunch of processes, and of course we want to run them one by one, so that to the user, it seems that these processes are running at the same time, and this is of course supported by what? Supported by the operating system, and through the term named the context switch, which is the key term that I ask you in your midterm. So right here, so the question is, explain the difference between the preemptive and non-preemptive scheduling. Okay, so this is about the categories for different CPU or process scheduling algorithm. And here we can get the description from the section 6.1.3. That is, a preemptive scheduling allows a process to be interrupted during its execution. Okay, so have its status saved and swapped out. And then for what? So that to release CPU to deal with the next process in the ready queue. Okay, and then while the non-preemptive scheduling does not allow a process to be interrupted, and the CPU will be released from the process only when, well, so two cases. So that is about the first case, the process switches from the running state to the waiting state. For example, when that process requests for I/O, so the speed of I/O is not tolerable by the speed of CPU. That's why we will put the process from where? From the running state into the waiting state and put it into the waiting queue, okay? And waiting for the I/O to finish. Or if a process is done, so what do we do? If a process is done, then so of course I will not allocate the CPU to you, and I will say, so please release the CPU for others to use, okay? Now, based on this description, let me ask you, so in your operating system, so you can count any operating system that you are using with, for example, maybe the Android, the iOS, the Mac OS, the Windows, Linux. Let me ask you, is your process scheduling algorithm in your operating systems like a preemptive or non-preemptive based on this description? Of course, it will be preemptive. That is, the OS has the right to pause and swap out a process and run the next. Okay, in that case, yes, this is of course the case. Preemptive scheduling. So this is hard, and this will create some like set efforts. For example, the data racing condition, which we don't want, but this is the foundation to support what? To support multi-processing. Okay, this is the foundation to support multi-processing so that we can have a better user experience. We don't need to wait a process to finish. Okay, and we don't want the CPU to be allocated just to one process because we have so many tasks running at the same time. Okay, and also recall that we actually learned how many algorithms of the scheduling algorithms. Let me recall. So I have the note here. So we actually learned 4 scheduling algorithms from actually, so I will tell you first 3 here. Okay, we actually learned from chapter 6. Okay, so 3 algorithms that we learned. Okay, so the first one, it will be what? It will be the first come, first serve. Guys, tell me for the first come, first serve. So what category should I place this into? Is that preemptive or non-preemptive? So this will be also non-preemptive for sure. Why is that? Well, first come, first serve. No one will interrupt you. You don't care about the priority. You don't care about the length. You just care about the order that as they arrive to the ready queue, to the CPU, right? And of course, this will be non-preemptive. Okay, preemptive. Okay, so this will be the non-preemptive. Okay. Now let me address the question. Is that a reason why processes have multiple cores? Well, so one good reason for processes to have multiple cores is we can run different processes at the same time because one core will be able to run one process. And of course, so when we talk about the cores from the CPU, so you are not amazed about the numbers. For example, so even for the, well, so now, so we have a, you can call we have a newcomer, or you can even call we have a somehow game changer here. Okay, so what is that? That's a new CPU released by Apple based on what? Based on the ARM structure, right? M1. Yes, that's right. But guys, for the computer science students, you want to observe and do more search before you fully transform your platform from the, let's say, so the Intel based. If you are a Mac user, or if you plan to get the newest Mac, which is based on the M1 CPU, you want to do more work to make sure that the G++ and other core utilities can be executed successfully on M1. Okay, and so of course, so software vendors, they will eventually catch up with this new CPU to support the M1, because this will be sold like with how many copies? Maybe millions copies, right? But now, so if you are relying on your computer to perform the core task, like compile a file, probably you want to wait a little bit, okay? Unless you are the iOS developer, which M1 is, so from the same house, so it will support the iOS compilation, so to a good extent. But for the C++, especially for the G++, you want to do more research. Okay, so this is what I heard, that the M1 and the G++. Now, so people are waiting on the new release from the G++ to make sure it will work perfectly on M1. Okay. And of course, so talking about the cores, that's not a big number, but consider the number of cores on GPU. Okay, so and you will be amazed like how many cores that you can consider from the GPU. It will be hundreds of thousands. Okay. All right, so to the, not a detailed number, but so I guess this is from what I not learned, but this is from what I heard. And that's why, so for lots of AI-based or data processing tasks, you want to have a strong GPU to support the data analysis and study, okay? Now, the next algorithm we learned from, you're welcome. So the next one we learned from the chapter 6. What's that? This will be the shortest job. Okay, shortest job first. Okay, for the shortest job first, and you can, so for this one, truly, I should put two things here. So it can be what? It can be non-preemptive. It can be non-preemptive. That is to say, so hey, I don't care about the whether you have a newer shortest job arrived to the queue or not. I will focus and finish what I have now. Okay, say that so I got 3 jobs. Say that one will take 3 seconds. Let's say so one will take 2 seconds and one will take 5 seconds. And of course, I will deal with the 2 seconds first. Okay, so the one in the middle. But if at the same time I get a new process which will demand only 1 second, I will not interrupt my 2 seconds task. I will let it finish, and then so I will run the next one. Okay, so for the shortest job first, it can be non-preemptive. That is, you just ignore the new arrival process, or it can be preemptive. Okay, so it can be preemptive, and it can be preemptive. And of course, when we are dealing with a preemptive algorithm, that is the one that I showed in class. So what is the name that we get to describe that algorithm? It is called the shortest remaining time first. Okay, you want to see, hey, so this algorithm that considers the shortest remaining time first, you want to see what? You want to keep an eye on the new arrival process. So if we get the remaining time, so if we get this one, you will say, hey, so I got a new process and I need to deal with it first, okay? And what is the abbreviation to that? Yeah, thanks. So it will be the shortest remaining time first, okay? So this is preemptive, okay? This is a preemptive. That depends. You can be preemptive, you can choose to be not preemptive, okay? And that depends on the variant of the shortest job. Okay, and the other algorithm that we learned, and of course we spent the whole class, was that is a round-robin algorithm. Okay, there's a round-robin algorithm, and for this RR algorithm, so what categories are placed to that? Is that preemptive or non-preemptive? Of course, it will be the preemptive, because we will allow a process to interrupt at the CPU quota. Say that we're running a process for 4 seconds now, so give it a break and switch to the next one. Okay, so that's why for this one, round robin, it is a preemptive. If the round robin is not preemptive, it becomes what? It will become the first come first serve, which is of no interest, right? So, and we will say round robin, we allow it to be preemptive so that we can pause the execution of a process and bring the next one from the queue. Okay. All right, this is the first question. And when you do the question, ask yourself preemptive. So now, so two notations, some preemptive and non-preemptive. So what do you want to know about it? Well, so you want to know about the description, the distinguish, and also you want to know, hey, so the application, like we learned the algorithm, which is which, okay? And then proceed to the next question. So let me see. This is saying that I consider the following set of processes which with the length of the CPU burst given in milliseconds, and the process are assumed to have arrived in the order of the 1, 2, 3, 4, 5, all at time 0. Okay, good. So this is a good sign. So we will just load them into the data structure, maybe the queue. Okay. Now it says draw 4 Gantt charts that illustrate the execution of these processes using the following scheduling algorithm. First come, first serve, and the shortest job first with the non-preemptive priority. The larger priority number implies a higher priority, and the RR with a quantum 2 here, okay? Now for this one, so I think this is a relatively easy question and with good probability, I will ask you something like that in the final exam, okay? And that is to say, so from the operating system, from this class, guys, we are almost to the last week of course, next week is the holiday break. We don't have any classes, okay? And we are almost at the end of the whole semester. Let me ask you, so when talking about the operating system, and how are you going to describe this class to others? Well, so maybe you will choose some adjective like boring or interesting, but let's say, so we need to cover one, notations, okay? Lots of notations being introduced into the operating system, and the preemptive is just one, okay? And the second, relationships, okay? So how they are going to interact, how these terms, they are going to interact to support each other. For example, we learned the context switch from chapter 3. And then so you will see, so maybe all the way through chapter 6 and all the way through chapter 7 and 8, maybe the 9. So how they are going to interact with each other to support the multi-programming environments that we can use. Okay, so this is the big topic because we're dealing with a complicated operating system or operating system concept. And then so maybe the next one is, hey, so do you see, or the third point, do you see lots of reflections of other computer science classes, for example, the algorithm class and the programming class? I hope the answer to these three questions are yes. Okay, and of course, so different person will have different answers, but I care about these three, and so my whole class, so it is constructed based on the three. So for each class, for each new chapter, I'm going to ask myself, hey, so what notations would you like to bring to your students, and how they are related to the previous covered topics? And so is that a reflection of something fun? For example, the algorithms from the, not from the operating system, algorithms from other programming classes? If the answer is yes, then so bring these topics in. And otherwise, for example, lots of topics, we don't have them covered. And of course, it's so easy that we just bring a bunch of slides and read it through and ask you to memorize these notations and ask you to copy and paste these notations in your final exam. Well, don't do that, okay? But the key point is I want you to understand these notations and bring them in your knowledge structure, and then see that talking about computer science, programming algorithms, and see these reflected in the core computer science class. Okay, so this will be my goal. And right here, although, yeah, so we can even bring this question and erase out many things, for example, processes, and just ask maybe a high schooler to draw the Gantt chart. Yes, the drawing part is not hard at all, but the key part is, do you see this Gantt chart? Do you see these Gantt charts reflecting the core ideas, for example, the preemptive, non-preemptive, and do you see that reflecting the algorithms? And can you write an algorithm to deal with that? Well, I hope the answer to these questions will be yes. And that is why you are a college student, not a high schooler anymore, okay? All right, go back here. Do I need to draw these Gantt charts? It will be a while, but I can. So because for the rest, let's see how many pages I get. I got this page 1, 2, 3, and 4. And I guess this question bugs you a lot, right? So because I received some emails saying that, okay, so can you talk more about this question, and I postpone and say that, okay, so I will have this one explained sometime. Okay, this one must be covered. Now, guys, for this one, so question number 5. So I will not run a pool, but question number 5, if you think, so please go over this question, and then so I will be happy to do that. So please let me know in the chat. Guys, now calling your answer in the chat. If you think I need to go over this question number 5, homework number 5, question 6.16, then so please let me know in the chat. You say yes, please go over this question, and I will comply. Okay, otherwise we will move to the next one, because to me, this one is not very hard. Okay, anyone? So the first call, do I need to go over this question? Second call? No, so I will say you anonymously approved this question. We can skip that. But feel free to let me know, okay? So truly, don't feel shy about, hey, so I don't want to waste the whole class time. No, you are part of the class. So there's nothing like the whole class time. And it makes sense we go over the question, okay? And then to this one, interesting. So homework 6, question 7.4. Hang on a second, this is homework 5. Yeah, homework 6. So why we have the homework question number and the chapter number off by 1? Well, that's a mystery. So it says consider logical address space. By the way, this is from chapter 7, which we talk about what? We talked about the main memory in chapter 7. Okay. So what are core notations in chapter 7? So I hope you can answer page and frame, right? So these two terms, we use them to represent what? The page for logic address and the logic memory, and then the frame for what? The frame for the physical memory, and they are related. They have the almost the one-to-one correspondence, and then until the next chapter, right? So right here, consider a logical address space of 64 pages. Okay, 64 pages, and of the 1024 words each. Okay, now guys, so someone, so when reading this question, have you wondered what is a word? What is a word? Guys, so tell me, what is a word? You say it's a Microsoft Word. No, it's not. Microsoft Word means the program that I'm running now, or process I'm running now. What is a word? You will say one word, guys. Okay, maybe, so if you are asking this question, so you should do the search bit, byte, word, and then so you will see data types and addressing models from here. And you will see, guys, so from these fundamental data types, from where? So from this page, Intel, okay, data types and addressing models. So what is a byte? A byte is 8 bits, right? So 1 byte is 8 bits. And here, guys, one word is how many? One word is 2 bytes that you can tell, right? And then, so that means one word is 16 bits. One word is 16 bits. And how about, well, so we have a next unit, which is the double word, and the next one will be the quad word, okay? Don't ask me where is the triple word. Guys, don't ask me where is the triple word. Why? Because you are taking the computer science class. We're not taking the counting class. Nothing like the triple words, okay? So 1, 2, 4, 8, 16. You don't get the number 3 here. Okay, so now from this description, we know one word is 16 bits, but truly this question, so you may be wondering, so do I need to worry about that? Well, so I will tell you, you don't need to worry about how many bits inside one word, okay? And I will tell you the reason later. Now let's read the question. Okay, so this is the first part, got 64 pages, and one page has 1024 words each. Okay, and then so this will play a next role in my explanation, and map onto a physical memory of 32 frames. Guys, so let me ask you, so when you see 32 frames and when you see 64 pages, so of course, these two, they are not the same, 64 versus 32. Let me ask you, so if one page has 1024 words, okay, how many words we have in a frame? Guys, how many words we have in a frame? So someone tell me 2048. Is that the answer? No, big no, that's not the answer. When we start the chapter 7, there's a big not an assumption. There is a big condition. That is, you are going to do what? You are going to use the same size for the page and frame. Recall that? Same size for the page and frame. You don't transform the size in the middle. That is a disaster. You don't want to do that. Okay. Same size for the page and the frame. Recall that what analogy that I gave you. The shipping container. That is the analogy I gave you, right? So right here, so 64 pages, each page 1024 words long, and 32 frames, each frame 1000, same size, 1024 words long. Okay, you must know that, and this is the condition we talk about the page and the frame. Otherwise, don't bother to set up the logic frame. My bad, don't bother to set up the logic page and just go ahead and use the frame, because you will get lost in the transforming in the middle. Okay, so right here, so okay, now let's read the real question. Besides the description, how many bits are there in the logical address? How many bits are there in the logical address? And then so let's do some math. So I get 64 pages, and inside of one page we have 1024 words. Okay, and one word is 16 bits. So you may arrive into this answer. Okay, so that is, I'm going to write it down. That is the 6. Why 6? Because 2 to the power of 6 is 64. You may get this answer. Okay, so you may get this temporary answer. Guys, don't write this down. This is not the final one. Okay, you may get this answer. Okay, 6 bits to represent each page, right? So you need 6 bits to represent each page. And for each page, you have how many? You have like a 2 to the power of 10, so which is 1024. Okay, so inside each page, you have this many units, so 1024 units, which you need the extra 10 bits to represent that. Okay, and then it is so tempting that you add the next one, which is 16 bits, because you do have the reason. One word. Okay, so one word is 16 bits. Okay, one word is 16 bits. Well, so if you get an answer like that, guys, so this is very close, very close. How close? Well, so I would say the first 2 parts or the first 2 expressions, they are correct. Okay, and you don't want to consider this part. Let me bring the menu so that I can strike out this line. You don't want to consider the fact that one bit is what? 1 bit, no, my bad. One word is 16 bits. Okay, and you may be wondering why you don't consider that. Well, because this is the word. Word will be the unit we use to represent the storage. We don't mark inside each bit which is which. Okay, recall that when we say the address for the memory, what are we talking about? We are talking about the address that you can use to specify the storage unit. If you choose to set the word as the storage unit, then so you can use that. Or if you choose to set the byte as the storage unit, you can go for that as well. But you don't set the bit as the storage unit. Why is that? Well, so if you need to get the fine control of each bit, well, then the space will be too large, and you don't want to like get the fine control of each bit. Okay, and then so maybe you will say, hey, so why don't we consider that? Because all I need to know is how can I identify the address for the storage unit. I don't need to look into the bits inside the storage unit. Okay, so the answer to the first question, so how many bits are there in the logical address? And the answer to this question, it will be 16 bits. Okay, and again here, you don't count what? You don't count the storage unit. You see that the word, I crossed it out because we don't want to count the storage unit here. We want to mark the address for the unit. We don't want to add the space or add the bits from the storage unit. We need the address to mark the storage unit. That's it. Okay, as long as you know which page and which word is that, so you are in good shape. And don't just add the address, or don't just add the 16 bits because we choose to use the word here. Okay, Now, I hope you don't add this line. So when you develop the answer, okay? Now, so it is the same case for the next one. Guys, this part is very confusing. So first, when I look at the answer, so I ask myself, why don't we count the word? Because one word, so that is 16 bits. Then, so if all we need to know is, hey, so please identify the address for the storage unit, which is a word, then so everything comes clear because we need to mark the storage unit. About how large is the storage unit, it is not our concern. We may use word, we may use quart words, and we may use the bytes for the storage, but we choose to not using that at all. Okay, we choose to not add the address, how many bits from there into the answer. Okay, is this part clear, guys? Okay, to the next one. So for the next one, you get the answer. It will be 15 bits. And why is that? Well, also because 2 to the power of 5 will be the 32. Okay, and then so for the rest, so it's the page, the size for the page and the frames, they are of the same size. So we got the 10 bits here. And when you add the 5 and the 10 together, you get 15 bits. Again, you don't consider the size for the storage unit because you need the address to the storage unit. You don't count what's inside the storage unit. Okay. And now after answering these two questions, hey, you see the logical address is greater than the physical address. How come that is the case? Well, so you can do that. Why? Because we have the technology called what? The virtual memory. You don't need necessarily have the same size of the logical to the physical. The logical can be fairly large. Okay, the logical can be fairly large, and to the physical, so it is so just the memory space that you have. So what if I need more? Well, so you learn some algorithms called the page replacement from the next chapter. Is that the case? Yes, that's the case. And actually, so I was like many years ago, I was a little bit shocked to see this number. Okay, so now let me try to search that out. Okay, so logical address for, well, guys, 8386. Someone tell me, so what is this 8386? Well, so that is an old CPU or ancient CPU. So how many years ago? Maybe more than 30 years ago, I guess, maybe more than 30, 40 years ago. Okay, now, so at the speed of the CPU transformation, so this is ancient, and you don't see much about the 83, 86, okay? Logic address capacity. Guys, how many years ago for this CPU? 30, 40 years ago, okay? Now you look at this number. So you say, what? 64 terabytes? Yes, 64 terabytes. That would be the logical space supported by a CPU like 30 or 40 years ago, okay? And then this would be the magical of we'll call it magical. This would be the power or the magical of using the logical address here. You don't need to truly have the 64 terabyte of the RAM. That would be very expensive, trust me. But you can assume in the logical space, this is the space that you can have for one program to run. And of course, this will satisfy all needs for what? For the program back to that time. Okay, so then you can take a look. So by using the logical and the physical address, by separating these two and just create a space that is sufficient to support the programs. How nice is that, right? And leave the rest like the page swap or the page replacement algorithm to the next chapter, okay? And about the physical address, you can tell it is up to 4 gigabytes at this time, okay? Up to 4 gigabytes here, okay? And then you know the reason why. Why is it up to 4 gigabytes? 2 to the power of 32, that is what? That is the 4 gigabytes, 32-bit system, okay, 32-bit memory address, and to support the 64 terabyte memory space, logical memory space, okay? All right, so that is when you're doing the question. So you can ask, well, so if these two are not the same, how we can resolve the issue these two are not the same? Well, so refer to the next chapter. Okay, so really the microprocessor and the microcontroller. Okay, yeah. So that's Is it related to microprocessor and microcontroller? Well, so remotely related, let's say this way, remotely related. And so I guess starting from 386, you have the memory controller embedded into the CPU. Is that the case? I'm not sure on that point because I don't have the sufficient hardware knowledge on answering the question. So whether these two are combined or not, I think so, because if I recall, like 286 it is separated, but to the 386 it's being embedded. So you can say it is remotely related to the, of course, for the logical memory, you need to have what? You need to have the hardware support. Okay, so that's why I get you the remotely related, because when we talk about the capacity or the support to the logical and the physical memory, we care about the bits that's being used. For example, 286, so it is 16 bits, and to the starting from the 386 all the way to the part of the Pentium 4, it is 32 bits, and starting from the late production of the Pentium 4 all the way to now, so you don't need the 64 bits for the memory. Okay, so that is why. So okay, so it is related, but we care about like how many bits for the CPU is that. Okay, all right, any questions on that? You don't count the bits from the storage because you want to mark the storage. Okay, and that's why you can use this info to represent the how many bits we need to find it. Okay. Okay, and to the next one. So it says the question also from the homework 6. It says assume that a 1 kilobyte, by the way, kilobyte, okay, not kilobits, kilobyte page size. What are the page numbers and offset for the following address reference? And given that all these numbers, they are what, hexadecimal coding. Yeah, so that's cool. So given that this is all decimal numbers, well, so what do you do? So you get 1 kilobyte, you get 1 kilobyte. And what is 1 kilobyte? 1 kilobyte page size. And let me ask you guys, when you see the addresses, and we're talking about the page size, when you see the addresses, two options, logical address versus physical address, which one you want to take? Of course, it will be the logical address because we're calculating the page number and we need to know about the page number. Okay, so for this one, the reason I bring my calculator here is I need to know what is the page and what is the offset. Okay, 3085 divided by 1024, and you get the answer 3. And that will be, for this address, you need to go to page number 3. And what is the offset, guys? What is the offset? Okay, so you use 3085 mod by 1024, and you get the offset. The offset will be 13. Okay, that is with the support from the programmer calculator. You can easily calculate that out. Okay, and if you don't have it, then maybe you would just do some multiplication to figure out the number as well. Okay, to the next one, and to be 24095 divided by 1024, and you get 41 as a page number, and 42095 mod by 1024, you get the offset. Offset is 1111 here. Okay, so to me, this question is fairly straightforward, and I hope you get it right. Okay, any questions on that? We good? Okay, to the next one, and this, how many questions I gave you in homework 6? 3 questions? Okay. So homework 6, question 3, 7.28 from that page. So consider the following segment table, guys. We mentioned about the segment. What is that? That is you want to you want to segment. You want to create segments inside the memory, so that so these segments will be utilized by what? Will be utilized by different programs, and we place a program there. And of course, so this is before the page, the logical address. Then so people use the segment to load multiple programs into the memory. Okay, and of course you don't see much segments now, but let's say that we have the segment Okay, and we have 1, 2, 3, 4, 5 segments from 0 to 4. Okay, and for each segment, you need to know what? You need to know the base address and you need to know the length. Okay, when you see that, of course, I'm expecting you to immediately reflect an important, you call it data structure, important data structure from any programming language that is array, right? So yeah, as the first one. And for the array, what do you need to know? You need to know the base address and the index. You may be wondering why the index starts from 0. Well, that is because we're talking about the offset to the base address, okay? So right here, let's see. So what are the physical addresses for the following logical addresses? This is a question about the logical address to the physical address transformation, okay? Now you will read, okay, so it's represented like, is this 0,430? You say, is that 0,430? No, it's not. This is the segment number 0. And about the offset, what is offset? 430. Okay, so offset is 430. So the first part, 0, 1, 2, 3, 4, they are what? They are the segment number. And about that, it is not the base, but this will be the offset that you are going to add to the base. Okay. Now for the first one, so what is the what is the physical address corresponding to this logical address? You will say, hey, so it is on segment 0, which is here, and then you are going to grab the base address, which is the 219, and add 219 to the offset. Okay, add 219 to the offset, and this is the answer you get, 649. Given that the offset, guys, the offset do not exceed the length. If you exceed the length, as you will see in the third case, so which is right here. Let's take a look, okay? Now, so of course, the calculation to the second one, it is easy. You grab the base address and add the offset, and you get the physical address. And to the third one, you say, hey, so this is an address on segment 2, and then you go to this table and get the base address for the segment 2, which is 90. Okay, and here the offset is 500. You see, easy, 90 plus 500, 590. That's the answer. No, it's not, because check the offset with the length. What is the maximum allowed offset that we can have here? Well, so it should be less than that by 1. Okay, so that is 100. And then, so check out this offset is 500. What do you say? For this address, you will reach what? You will reach the illegal reference trapped by the operating system. Why this address is illegal? Because it goes exceeding the maximum length that we can have for this segment. You cannot exceed the boundary for the segment. Otherwise, that is a memory violation and your program will be killed by the operating system, okay, to protect others. So, and we have the last case as well. So right here, segment 4, and the maximum length 96, and you want to access 112, which is not allowed by the OS, and that's why you get the illegal reference as well. Okay, now this is a simple question. All you need to know is how you read that. It's not like a 110, okay, and you don't put a comma for the 100 position. Okay, you put it for the 1000, but yeah, so you need to know this is the segment number, and it will be the offset, and how you add the offset to the base, and make sure it is offset, it's not exceeding the length, will be the key point to get this question done. Okay. All right, so to the next chapter, chapter 7. Here we get chapter 8. So from homework 7, so we get how many questions? I believe we have 2 questions, and this one looks so familiar. Do I need to go over it again? I hope the answer is no. Okay, but you can check the answer here. For the list recently used, we got an 18 segment. Not segmentation. We got an 18 page faults, and for the first in, first come, or first come, first serve, or first in, first out, we get 17 page faults. Okay, and for the optimal, so this number smaller than the rest. At least it should be smaller or equal to the rest. So we get 13 page faults. Okay, now this will be the answer, and I will skip that. Okay, coming to the point of this one. This is an interesting one, and it worth the time. So Let's see. So question 8.22 from the page 427. The following page table is for a system with 16-bit virtual and physical addresses with like a 4K bytes pages. Okay. Now, so you are telling me that we use 16 bits to represent. We use 16 bits to represent the memory. Okay. Both for physical and for the virtual, okay, which is good. Now, so logical, virtual, and physical, virtuals in the middle, okay? Now, for each page, we have how long? We have 4K or 4096 bytes for the storage, okay? And the reference bit is set to 1 when the page has been referenced, and periodically a thread zeroes out all values of the reference bits. So clear the reference bit and prepare for the next use. A dash for the page frame. Well, so here's a page frame. A dash for the page frame. By the way, so here it says page frame, a weird term, and to me this is just called what? This is just called the frame column, okay? And this is the page column because we're talking about what? We're talking about a page table. And we say, where is the virtual memory? Well, the virtual memory part is about managing the page table here. And that's why we get the two info, page info and the frame info. And of course, we get the reference bit, and we will set the reference bit according to the access here, okay? Now, a dash for the page frame or for the frame indicates the page is not in the memory. So what do you do there? So you want to load the page when requested. And then the page replacement algorithm is localized LRU, least recently used, and for the localized version. So I don't think our textbook gives a full description of the localized LRU, but somehow very similar LRU or the standard LRU is being introduced, and some variants, and all numbers are provided in decimal. By the way, so for this question, we truly don't need to know about what's being localized here. Okay, maybe just the one that is satisfied to this system here. And then, so let's see the page table, and we get the page numbers, and we get the frame numbers, and we get the reference bits all clear to 0. And now, so let's read the first part. Part A, convert the following virtual addresses in hexadecimal to the equivalent physical addresses. And you may provide the answers in either hexadecimal or decimal. And also set the reference bit for the appropriate entry in the page table, okay? Now it seems that I need to draw something on this table. Okay, I need to draw something on this table, not a problem. And I will just copy this table while you're still here and paste it here. Okay, and then so according to the design, maybe I will choose this design, maybe this one. Okay, yeah, just get some good ideas. Okay, and then so we need to do what? We need to convert the address. Convert the following virtual addresses in hexadecimal to the equivalent physical addresses. How can I do that? Well, I guess I need to know about the link between the page and the frame. Okay, let's take a look. So, what information I need for the conversion? I need to know how large is each page. Okay, that is a 4096. Now bring out the calculator, guys. 4096, this is in decimal number. 4096. Okay, what is the corresponding hexadecimal number, guys? Hexadecimal number, you read 1000. No, it's not 1000. It is 1000 in hexadecimal number. Okay, don't read it as 1000. 1000, so we are so get used to the number system, which is the decimal in the daily life, and you don't want to put an incorrect link between this number, hexadecimal number, to our daily life 1000. Okay, now this would be saying that if we represent the address, or if we represent the size, of the page in hexadecimal, it will be 1000. Okay, maybe quietly read it 1000 because this is easier, right? And then, so how we can convert this address? Well, this is the what? This is the virtual address, or you can think this is the logical address. and how we can convert it into the physical address. Well, guys, let me ask you this, okay? Now, so can we add two hexadecimal numbers? Can we add two hexadecimal numbers? So recall, you learned from previous class, can we add two hexadecimal numbers? Yes, we may, right? For example, A plus B, what do you get? A plus B, what do you get? What do you get from A plus B? A plus B, you get, you say, so I got 15, right? No, it's not 15, it is 15. Okay, it is 15. So use this calculator here. So don't convert it into the decimal. Yes, A is 10, B is 11. So in decimal, and then you get 21. Okay, you get 15 in A. Can we multiply two hex numbers? Answer would be yes. Yeah, go ahead and multiply two decimal numbers. For example, A times B, and of course you get the answer, right? So 10 times 11, what do you get? You get 110, right? So 110 in decimal. And what is that in hexadecimal? It will be the 6e here. As you can tell, the decimal number it is 110. Okay, and then you click the hexadecimal, it is 6e. Yes. Now, can we divide two hexadecimal numbers? Can we divide two hexadecimal numbers? Yes, you may, for sure. Okay. Now you know that. Okay, so if I get AA divided by A, what is the answer, guys? AA divided by A, what is the answer? You say 11. No. Is that 11? No. This is a 1 hexadecimal. Okay, don't read it like the daily way that we read the decimal number. It is 1 and 1. Okay. Now, if we can divide you don't consider divided by 0. If we can divide two hexadecimal numbers, then the question will become very easy here. Okay, so the answer to this question, it will become fairly easy. Why is that? You get a hexadecimal number. You know how large is a page in hexadecimal. What is this number again? What is this number again? So not in this number in decimal, it is 1000 in hexadecimal. Okay, and recall this number 1000. I'm going to have it copy it. Okay, 100. And then so to get this question, it will become fairly easy. And how to do that? Well, I need to know about the physical address, right? So now, so I have what? All I have. Okay, so who triggered this dictator function? Dictation function, not dictator, dictation function. How can I stop that? I know I hit a key, but stop dictation. You're not. Here we go. What is the shortcut that I don't press it again? Alt and this key. Okay. Okay, now so I just show you a tip to quickly write your next essay, right? You can trigger the dictation and then so just read everything through that comes from your mind. And then so it will be unique and it will, with a good probability you get a high score. Okay, don't take it for guaranteed. So, and don't tell your English class teacher if you're still taking, but I guess for most of you not. Okay, guys, how can I calculate the address? What I got here, so that is a E 1 to C. I want to divide by this 1000. Okay, and I got this number E. What is that? What is this number? Maybe I should write this down. And this is a logical virtual address to the physical address. Okay, now what do we do? The first step, divide logical address by what? By the page size. Okay, so either both in decimal or both in hexadecimal. Okay, now this will ease your work. Don't convert into another system. Okay, so that is not convenient. And then, so what do you get? Then, so the page number is the quotient. Okay, so the page number is the quotient from the division. Okay, now look at here. I get the E as the quotient from this division. Okay, and what that corresponds to? What does that correspond to? That will correspond to what number? What is E? What is E in decimal? It will be 14. Okay, 14 decimal. And then you are going to say this is the 14 and it corresponds to the page frame. What is the page frame? The page frame is 3. And how can I represent the 3 in hexadecimal? Well, it is 3, both decimal and hexadecimal. Okay, and how about the rest? How about the remainder 1 to C? Don't touch the remainder. Remainder will be the offset. Okay, remainder will be the offset. So the answer to this question, what do you do? You will say, hey, according to the quotient, according to the page frame table, I get that it must be on the frame 3 with the offset 1 to C here. So I'm going to write the answer as 0x3 1 to C here. Okay, now this will be the answer to the first question. And also, since I need to maintain this reference bit table, I need to draw something and grab my pen. And which one we just accessed? This one we just accessed. So mark it as 1. Okay. And to the next one, 3A9D, 3A9D. So then you quickly do the math. Okay, so this number divided by 1,000. Did I say 1,000? No, 1000. Okay, so 1 3 zeros. And what do you get? You get the page number to be 3 here. And what is the corresponding page frame? The page frame, or I should say what is the corresponding frame? It will be 10, okay? But I'm going to write the 10 in hexadecimal. No, you are going to write A. That's why you have this one converted to A here, followed by the remainder, which is the offset, which is A9D, and you get AA9D for that, okay? And then so also in this table, I just accessed this page, so mark this with 1, okay? Now the next one, A9D9. So, so the quotient will be A, which is 10 in this page, okay? And that corresponds to the frame 5. So you are going to convert that into the 5 and with the remainder 9D9 here, okay? Okay, guys, I'm off time. So if you have to go, so feel free to go now and then so check out my video later. But if you don't have the immediate class or if you have some spare time, then so please stay in our meeting and I'm going to finish this one fast. Okay. Now for this conversion, so this will be the way that we do that. And I will need to just mark which one. So this 5, okay, 59D, so which is right here to be what? To be the 1. And I need to mark for the rest 2 as well. Okay. Now, the next question is using the above addresses as a guide, provide an example of a logical address in hexadecimal that will result a page fault. And this is the easy one. What is a page fault? A page fault is when we want to access the corresponding page and we figure out it's not there, not in the physical memory, not loaded. What do we do? Well, so we will replace a page, right? So we will load the page. So if we say, hey, so right here inside this figure, I would say, so any addresses inside the page 4, inside the page 8, inside the page 12 and 13, they will generate a page fault. And then so maybe we'll just write one. For example, 4000, that will generate the page fault. Okay, because the page 4 is not loaded into the memory. And 4010, that will have the page fault as well. You can choose from any sections. So from the page 4, 8, 12, or 13, that will have the page fault. Okay. Now the next one, from what set of a page frame will the LRU page replacement algorithm choose in resolving a page fault? And you would say any page table entries that have a reference bit of 0. And then this will do what? Let's say, so this is asking about the LRU and what is the criteria for the LRU to choose a page to replace, okay? And of course, anything marked with 0, and of course, we will have something marked as 1. That means we recently visited them, so please do not change them, okay? So if you see something 0, then replace it with the desired page that will get the work done, okay? Now, so to this part, from what set of a page frames, well, so we will say any frames that has a reference bit as 0, we will replace them. Okay, and of course, for this one, you will need to write down this answer here, and it is because you have these pages accessed from step 1, and then so we should have them marked in our reference bit, so that you just choose the ones that is not marked here. Okay, and you get the following. Okay. All right, so I'm sorry I'm over time for 10 minutes today, so I didn't plan for that, but I hope you get the major part of the homework solutions, and especially for these questions. So because, so this kind of question, they are a good reflection of what we learn, and they are important to not immediately important, but they're important to know as a foundation for any CS students or related majors. That's why. So I should have it explained at some certain point, and I hope that the last question makes much sense after the explanation. Okay. All right. So that is all for today. We don't have any classes next week. No homework or weekly summary due. So you can enjoy the holiday break and always be safe. Okay. And thank you so much. And I will see you the week on December the 1st. Okay. Thank you. Bye-bye.